The new section is entitled Circles. What is the definition of a circle? Students always tell me it finishes where it starts. So it starts here and it finishes there. And that lived up to what they said. Problem is, that's not a circle. Saying it's round is not a circle. Well, think about how you draw a circle with, what is it, a compass or a protractor? I think a compass. Well, basically, you put your needle here, you open up the compass to a certain distance. That distance is R. And then you twirl this around. It generates a circle. Basically, a circle it is the set of all points, a fixed distance, from a fixed point. This fixed point is the center, and the fixed distance, that's the radius. Here's a fixed point, and you have some distance, 2 inches. This point gets to be on the circle because that distance is 2 inches. This point gets to be on the circle because that distance is 2 inches. This point gets to be on the circle because that distance is 2 inches. This point does not get to be on the circle because that distance is not 2 inches. It's all the points 2 inches away from the center. And each of these distances from the center to the circle is the radius. That is the definition. So, I immediately think of the distance formula now. Let's write it higher. If the center of a circle is h, k, and don't ask me why they choose to usually always use h and k as the center of a circle. The center is hk, and the radius is r. Now remember, d, the distance is the square root of the change in x squared plus the change in y squared. Well, if I square the left side, I get d squared. And if I square the right side, I just get what's underneath the square root sign. And in this problem, we're going to do that. That is, we're going to find the distance squared. Okay. So now, here is the center, hk. Now, how does this point xy come to be on the circle? How does that point xy get to hang out on the circle? The answer is very, very simple. The distance better be r. This distance should be r. Okay, well, what is the distance between here and here? Well, it's x minus x minus x, this x minus that x squared, plus this y minus that y squared, normally square root. And this is equal to the distance r. Well, for circles, for one reason or another, they don't like it that way. They like to square both sides. You square the right side, you will get r squared. You square the left side, you get this. This here is the equation of a circle with center HK and the radius is r. And all I did was use the distance formula and the definition of a circle. How does a point get to hang out on a circle whose center is HK and the radius is r? Well, here's the center. How does that point get to hang out on the circle or to be on the circle? Oh, the distance from the center to it must be r. And that's it. So I used the distance formula and it all came together. But in this section, we're not going to talk a lot about equations of circles. I'm going to lay down the groundwork. I'm going to talk about some definition. What are concentric circles? Those are circles that have the same center. They have the same center. That's the center. You have that circle, fairly small one, and a bigger one. You can draw circles all day long with the same center. Very small one, a little bit bigger, very big, mediocre. Can do this all day long. Concentric circles are two circles are said to be concentric if they have the same center. 22 circles are said to be concentric if they all have the same the same center. Congruent circles. Two circles are said to be congruent. They have the same radius. It just means same radius. Two or more circles with the same radius. Two or more circles with the same radius. Interior points. Interior points. Exterior points. If they're inside the circle, they are interior. Interior going to be red. Those are interior. They are inside the circle. Exterior, I'm going to put in green. These are exterior points. They are exterior to the circle, outside. In is very clear to me. Interior is very clear. Why? Because it literally uses the word in. It has the word in. Since interior was red, let's underline it with red. Interior. Me, I would have named exterior outerior. Outside. But I wasn't the one they asked. So you have interior points, you have exterior points of a circle. Interior points of a circle are inside the circle, and exterior points are outside the circle. Now, let's go a little bit further with interior and exterior. The radius is r. What can you tell me about interior points? And the thing is, if you go from the center to these points, the distances all have one thing in common. And the distances are less than r. So let's call a point xy. If the distance from from the center to a point xy, if this distance is less than r, then the point xy is an interior point. If instead of being less than, if the distance from the center to the point xy is greater than r, then the point xy is an exterior point. What if the distance is r? If the distance between the center and xy is r, then xy is not exterior to the circle, it's not interior to the circle. The point is on the circle. After all points that are r units away from the center is on the circle. Inside, on the plane, on a whiteboard, on a blackboard, on a wall, on the floor, on your paper. If you start going into 3 dimensions, that definition I gave you earlier for a circle will become a sphere. Take your basketball, find the dead center of the basketball, measure the distance between that center to any point on the on the basketball, and it will be the same. But we're just 2 dimensions, not 3 dimensions. This is 2-dimensional geometry, so I'm not really mentioning the word plane. Some people out there may say a lot of my definitions are off because I'm not saying the plane. Well, it's understood that everything we're doing, unless otherwise stated, is on or plane. So we talked about interior points, we talked about exterior points. Let's talk about a chord. A chord. It's a line segment that goes from one point of a circle to another point of a circle. A line segment that goes from one point of a circle, goes from one point on a circle, goes from one point on a circle to another point on a circle. So basically, you pick 2 points on a circle and you draw the line that connects them. That is a chord. From here to here is a chord. From here to here is a chord. And here's the center. Well, from here to here is a chord. That's also a chord. Any point, any line segment that goes from one point of a circle to another point of a circle, that is a chord. This is not a chord, because it may have started from one point of a circle, but it didn't go to another. It stopped right dead in the middle. If it continued, it's a chord. It's starting from a point on a circle. It looks like a chord, but it is not a chord because it didn't end at another point of a circle. It was too long. Make it shorter, it is a chord. There's a special name for the chord that goes through the center. A chord that goes through the center of a circle is called a diameter. Any line segment that originates on one point of a circle, ends at another point on the circle, and crosses the center is a diameter. It's a chord that crosses the center. That's the definition of a circle. Sorry, of a chord. Although I'm no historian, but although I'm pretty sure people knew that the area of a circle was equal to pi r squared long before calculus. If you take calculus 2 in particular, second semester calculus, you will be able to prove that the area of a circle is pi r squared. The circumference of a circle. That's like perimeter, but for circle. It's how far around. How far around. That is, if you took a string and you started it here and you laid it out as a perfectly round circle and it ends there, if you cut the string and lie it flat, how long is it? How long is it? And the answer is it's 2 pi times the radius. Remember, here's a circle, center, to a point on the circle, that's the radius. And if I continue the straight line the other way, that's another radius. Each of these are r. Well, if you add them together, you get 2r, but then you have a chord that goes from one end of a circle, from one point of a circle, to another, and it crosses the center. That's the diameter. D for diameter. So instead of, remember, this is multiplication. 2 times pi times r. That's the same thing as 2 times r times pi. And 2r is d. D pi, but to be honest, most people would write pi d. So we now have 2 formulas for the circumference of a circle. Now, if you take the area, which is pi r squared, and you divide it by the circumference, which is 2 pi r. The pi's cancel. Well, this is not what I wanted. Get r over 2. This is interesting. Whenever you divide the area of a circle by the circumference, you get r over 2. Always. So that's a nice formula to know. So if somebody gives you the area and the circumference, you divide the two, and now you have half the radius. Just double it to get the radius. Just double it. Okay? You know, if the area divided by the circumference is 7, then r would be 2 times 7. So I guess what I was trying to get was this. We know that the circumference is pi times d. If I divide both sides by d, I get pi. Any circle, if you take the distance all the way around and divide it by the diameter, amazingly, it's just amazing, you'll always get pi. Some people define pi that way. Okay, if you have this little bitty circle, if you've calculated the distance around it, and you divide it by this little length diameter, you would get pi. Exactly. If you take this really big circle and you measure the distance around it, circumference, and divided it by this distance, there's no two ways about it. You will get pi. You will get pi. No matter what the circle is, the circumference divided by the diameter always gives the number pi. Okay. Now, there are a few theorems that one needs to know when it comes to circles and chords. Theorem, call it number 1. If a radius is perpendicular to a chord, then it bisects the chord. Then it bisects the chord. Okay. What is this saying and how do we prove it? Here is a chord. Here is the center. Now, I can draw many radiuses, which are called radii. If the radius just happens to be perpendicular to the chord, here's the chord, here's the radius, because there's the center, then these two are equal if they are right angles. Okay. Now, how would you prove such a thing? Okay. First, you go like this, and oops. And you would go like that. Like that. Those two red lines are equal in length because they go from the center to a point on the circle. They are called radii. Now I'm going to proceed to show that these two triangles are congruent. The left triangle and the right triangle. That big triangle I cut in half, left and right. Call this point D and A and B. Well, clearly CD is in common in both of these. Now, can't forget your theorems. We have two right triangles, and the hypotenuses are equal. And one of the legs, the hypotenuses are congruent. And one of the legs are congruent. They have one pair of congruent legs. Well, by the hypotenuse leg theorem, that's only for right triangles. After all, you can't talk about hypotenuses unless you're talking about right triangles anyways. But by the high leg theorem, by the hypotenuse leg theorem, we have congruent hypotenuses and one pair of congruent legs. By the high leg theorem, these two triangles are congruent. Okay? That means those third sides are equal. Corresponding parts of congruent triangles are congruent. So yes, it does bisect it. Okay, let's reverse this theorem. Theorem number 2. THM is theorem. Theorem number 2. If a radius bisects a chord, then the radius is perpendicular to the chord. If a radius bisects a chord, then the radius, US, the radius is perpendicular to the chord. Okay, what is this saying? You have a chord, and here's the center of the circle. Now you have many radii. You can have this one, or this one, or this one, or that one, or that one. Infinitely many. But we want the one that goes right dead in the center of that bottom chord. So let me erase this, draw it again without all those extra lines, extra radii. Here's the center, and here's the chord. Oops, the circle didn't come out. There's the circle, the center, and we have our chord. Okay. Now, here is the dead center of the chord, the midpoint. If you draw the radii that bisects that chord, that is, these two are equal, that is these two lines, the red line, the radius, and the green line, the chord, are perpendicular. These are perpendicular. And how you would show this is to draw these two legs. So those are equal. Let me put two slashes, because these ones on the bottom have one slash, and those are equal. By SSS, these triangles are congruent. The left one and the right one, like before. Okay, well that means angle 1 and angle 2 are corresponding angles. Why? because they are made up of 1 slash and 2 slashes in triangle 1. In triangle 2, the angle I numbered number 2 is made up of 1 slash and 2 slashes. But 180 degrees, they lie on a straight line. Angle 1 and angle 2, they lie on a straight line. And if so they add up to 180. Well, if they happen to be equal, then my picture's off. It turns out that these angles are both 90 degrees. Okay, angle 1 and angle 2 must add up to 180 and be equal to one another. What two numbers add up to 180 and the two numbers are the same? 90 and 90. Okay, so that's true. So basically, if the radius bisects the chord, they're perpendicular. If the radius is perpendicular to the chord, it bisects. You get both for the same amount of money. You have a radius and you have a chord. Either the chord is perpendicular, either the radius and the chord are perpendicular and the radius bisected the chord, or neither. So again, given a chord and a radius, you get both or none. The chord is perpendicular, the radius is perpendicular to the chord, and it cut it into two equal parts, or it didn't do either of the two. You can't have one without the other. Okay? This chord right here, this radius right here, it cut the chord into two equal parts, and it's right angles. This chord, to be honest, it did not cut, Ooh, I'm doing this pretty badly, Let me try it again. That was not a radii. It has to come from the center. Here's the center, and here's a chord. Either both, here's the circle, and there's the center. Chord and a radius. Both of these statements will be true, or none of them will be true. This radii is either perpendicular to the chord and bisects the chord into two equal parts, or it did neither of those. In this case, it looks like it didn't do any of them. This angle does not look like a right angle, and this length here and that length there, they sure don't look equal to me. But over here, here's the center, here's a chord, this radii, it is perpendicular and it does bisect the line segment. You get both for your money, or you get none. It's an all or none deal. So kind of remember those two theorems. They come as a pair. Remember, excuse me. Remember that those two theorems, they come as a pair. Now, you even have a third one. You have a third theorem. And this theorem says you have a chord, and you go to the center, and then you go up perpendicular. Or, if the chord's up here, you go to the center, you go down perpendicular. So you go up and down, okay? It crosses the center. That chord crosses the center. The perpendicular bisector of a chord crosses the center. That is the theorem. You have a circle, you have a chord. Go to the dead center of the chord. Go perpendicular to it. You cross the center somewhere. The perpendicular bisector of a chord crosses the center of the circle. That, of course, being the symbol for circle. Now, just want to say one quick thing. Every time, or maybe one exception, when I drew the chord, I drew it horizontally. And I said things like, if this is a right angle, well then those are equal, or if these are equal, this is a right angle. But a circle has symmetry right through the center. If I rotated this circle with chords and all, well then I get that picture. I get the same picture. These two are equal, and those are right angles. Or these two are not equal, and those are not right angles. Okay, so it doesn't matter. You know, somebody gives me this picture, and for whatever reason, it's troubling me. I'm not seeing it. I would rotate it this way, and then look at that picture. They're the same picture. Just turn the paper. Turn your head a little bit. These two are the same picture. These two, it's a circle. They're the same picture. Just because you rotate it doesn't mean anything changes. Look at a quarter. If you rotate a quarter, did it really change? Looks exactly the same. Now, I want to give one silly definition. You have a center and you have a chord. Now, you don't even need a circle. For this definition. If you have a line segment or even a line that goes in both directions forever, or a ray where only one end goes forever, doesn't matter. If you have a point, excuse me, the distance from the point to the line is always the shortest distance. It's the one that goes at a right angle. And since we are on a circle, it will even, since this is a radii that met a chord at a right angle, it will even bisect it. So the distance from the center of the circle to a chord is the measure of the perpendicular line segment from the center to the chord. That's the distance. That's the distance. What is the distance from that point, the center of a circle, to this chord? The answer is it's the shortest distance, which happens to be the perpendicular bisector. But it's only the portion, it's only the portion that I erased. It's only the portion that goes from the center to the chord. The chord is what's in green. That's the distance. Okay. That should really be the last definition. So basically, if you have a circle centered at O, it goes to A goes to A and B. So we want to prove that triangle AOB is isosceles, and we also want to prove that angle A is equal to angle B. So let us be clear what we just did. We have a circle. Pick any 2 points on the circle, those 2. And then using the center and those 2 points, make a triangle. No matter what the circle is. No matter what 2 points you pick. Pick these 2 points and the center. Make a triangle. I'm claiming that all these triangles are isosceles, and those angles, these 2 angles, and these 2 angles, and those 2 angles, they're equal. And to show that it's isosceles is as easy as going like this and like that. Because AO is the radius. BO is the radius. All radii of a circle are congruent. Okay, so those 2 angles, these 2 sides are the same. And you know what? The opposite angles are equal. These 2 sides are the same, because that's the radii and that's the radii. And the opposite sides, the opposite angles to these sides are equal. This side and that side are the same. This is the radii and that's the radii. The opposite angles are equal. Always. Any circle, pick any 2 points other than pick any 2 points that don't lie on a diameter, and pick the center. Isosceles, those are equal. Now, why did I say not to pick a point? Pick 2 points that lie on a diameter. And the reason is, if you pick this point, and that's the center, I don't really see a triangle. If you pick the points a little bit above, well then, there's a triangle up there. Another words to use notation or language taught on this video. If you have 3 points that do not lie on a straight line, 3 points that are not collinear, you can draw a triangle. But if they are collinear, here's one leg of the triangle, there's the second one, but where's the third one? If this is 180 degrees, there is no third side. But once they're not collinear, this one goes over here. Triangle. And that's exactly what happens if you pick a diameter. If you pick 2 points that are a diameter, well then it crosses the center. So the 3 vertices of the triangle, they lie on a line. because there is no triangle. Okay, but that's a nice theorem to know, that any triangle that uses the center and 2 points on the circle as vertices, any circle that has 2 points as a vertex, as vertices, and the center, and here's the circle. 2 points are on the circle and the center, and they're not collinear. That is, these 2 points don't lie on a diameter. You get a triangle, and it's isosceles. I said that like 9 times. It's good to know that. It's pretty neat. Suppose you have a circle, and you take these two, here's the center, you take these 2 points on their diameter, and you go like this. They meet somewhere right there. Actually, let's suppose this is not the center. Let's suppose that's not the center. Maybe the center is here. Okay. So, you're given the OM is a median. Oh. Sorry about that. Alright, so you have R and S and T and the center O and the point P. And you're given that PR is perpendicular, and you're given this line. You're given that PR is perpendicular to ST. That is, that's the right angle, and O is the center. And you want to prove that angle S is equal to angle T. Okay. Now, what do we know? We know that we have 2 triangles, the upper one and the lower one, and the big one. STP is the big one. Now, we have a right angle here, we have a right angle here. Now, keep in mind that this radii crossed at a right angle. I mean, I could extend this line. It doesn't matter. I could extend it beyond R to the left. It is a radii, and it crossed, it crossed ST at a right angle. Oh, that means SR and TR are equal. And clearly, RP equals itself. Well, we have, in triangle 1 and 2, we have one pair of congruent sides, and we have our second pair of congruent sides, and right in the middle of those 2 sides, we have equal angles. So by SAS, the triangle 1 and triangle 2 are congruent. Well, opposite, the sides that have the X in it, side X, opposite it, those angles must be corresponding angles and hence equal. So that theorem is done, or that proof is done. see a nice problem to do. Alright, so we have this circle and we have that circle. And I'm not saying that the radii are equal. In fact, that's what we want to prove. And inside, you have this isosceles trapezoid. You have an isosceles trapezoid. And what you want to prove is that these two circles, circle P is congruent to circle Q. Prove this. Prove that. That just means that their radii are the same. Okay? Which means that PS and RQ would have to be the same. But by definition of isosceles trapezoid, they're the same. I mean, that's the proof, in my opinion. Isosceles, isosceles triangle, their non-parallel sides are equal in lengths. These two sides are equal in lengths. The other two are parallel. The opposite sides are equal in lengths. That's a property of isosceles triangle. So PS equals RQ. But PS, it goes from the center, draw it cleaner. PS goes from the center of the first circle to a point on the left-hand circle. That is, PS is a radius. QR goes from the center of a circle to a point on the circle. So QR is a radius of circle Q. But they're equal in lengths. PS, RQ equal in lengths. Done. Those two circles are in fact congruent. Remember, you have to know your definitions. Two triangles are congruent if they have the same lengths. Suppose we have this. You have a circle. The center is Q. You have this line, this line, this line, and that line. Let's label it P, Q, R, S, and T. And all you're given is, other than the circle as drawn, is QS is perpendicular to RS. That is given. And you want to prove that TQ bisects angle RTS. Well, RTS is that big angle. I want to show that TQ bisected it. Okay. Well, we have that QT, and RS are perpendicular. Well, that means right angles. Okay. That means right angles. And it means that these two are equal. And clearly, so we have two triangles, the upper one and the lower one. And PT, they're equal to one another. PT equals itself. So, in the top triangle and the lower triangle, we have one pair of congruent sides and a second pair of congruent sides. And the angle right in the middle of these two sides, this side and this side, they meet at this angle. The angle in the middle are equal. So by side, angle, side, these two triangles are in fact congruent. Okay, now corresponding parts. We'll immediately go to here and here, but I have to argue why those are equal. And they are. They're both opposite the side with one slash. So by corresponding parts of congruent triangles, these two angles are equal. Therefore, TQ must have bisected that big angle. It must have bisected that big angle. It cut it into two equal parts. They're all basically using those three theorems and some of these definitions. All right. So now we want to prove that we have a parallelogram. We are given that circle A is in fact congruent to circle B. That is, these two circles definitely have the same radius. One centered at A, the other one centered at B. Oops, not clear what happened, but we can fix this. Okay, there it is. And for simplicity, AB, CD. And we're given that the two circles are in fact are congruent, and that AD is parallel to BC. And what we want to prove is that we want to prove that ABCD is a parallelogram, which just means that opposite sides are congruent and parallel. So we know that those two are parallel. That's given, and they're equal in length because they're both radii, and we're told that they are congruent. That means the radiuses are the same. The radii are equal to one another. Okay. question is that enough? If you have two sides that are the same length and they're parallel, then you have a parallelogram. There's no way out of it. If two sides are parallel and they're the same length, when you draw the other two sides, that's a parallelogram. That's enough. We're done. Do not be afraid of these problems. Do not be afraid of these problems. If we were going to write this up in a statement reason format, statements, reasons, well, statement 1 is the given. Statement number 2. AD is congruent to BC. Congruent circles have congruent radii. Okay. So we've already stated that the two lines are parallel. We just stated that those same two sides are equal in length. Number 3, ABCD is a parallelogram. ABCD is a parallelogram. In a four-sided figure, in a four-sided polygon, if one pair of opposite sides, let me finish up here, please, are both parallel and congruent, then this polygon is a parallelogram. As a student, I'd be thrilled to be given such an easy problem. Let us try one more. It looks evil, it looks intimidating, but it's a piece of cake. A, B, C, D, center is O. Okay, so you're given diameter BC. It's a chord that goes through the center. You are given that AB and CD are parallel. And you want to conclude, you want to prove that AB, CD, same length, congruent. So, the first thing I would say is parallel lines. Those two are equal. Those two are equal. And then, let me use a different color to show that it was added afterwards. I go like this, I go like that. Those two sides are equal because they're a radius. In fact, I have triangle 1 up here, and I have another triangle down here. And you know what? Those two are equal. Those four are equal because they're all radii. They go from the center to a point on the circle. Okay, so that those green angles in triangle 2, angle D and angle C are equal. So that's also green. In triangle 1, angle A and B are equal, but angle B is green. That is, it equaled angle C. In fact, those four angles are equal. In fact, that green line that I drew, that goes from A to O and then from O to D, I won't swear to it, but I would think that would be a straight line. I would think that would be a straight line. But doesn't matter. Alright, so, and of course, we do have we have to be careful there. I didn't say yet that was this. I wanted to say opposite angles are equal, but you need straight lines. Oh, of course the opposite sides are equal. This is by the no-choice theorem. If two triangles have two paracongruent angles, then the third ones have to be congruent. Which means that red line has to be straight. That red line has to be straight. Because only there is a straight line. This is like BC. BC is clearly a straight line. The question is AD a straight line? Well, the only way those two angles would be equal is if this is a straight line. The only way those two opposite angles will be equal is if that's the straight line. Because if it is a straight line, they're equal. But if in fact it really went like that, well then no. This angle is smaller than what it needs to be to equal that other angle. So yeah, it is a straight line. So basically I have three angles are the same. They all have two sides that are the same. Yeah, these are congruent triangles. So these sides must be equal. Those sides must be equal. Okay, that completes this section on the circle. It's a long section. I hope you enjoyed it.